Okay, so let's get started. Today we will talk about LAN protocols and in particular about Ethernet and a little bit on how Ethernet systems are configured and working today. So it will be a little bit of history and a little bit of the current stuff here. Let's go on here. Review, we know a local area network is basically an area which is limited in physical extent. It's typically used over a broadcast medium, which means that we need medium access control. Hosts are moved around. We have a network interface cards which have physical addresses. And transmission over wide medium is usually close to error-free. We don't need so much sophisticated error control for this, but we need that for Wi-Fi. We'll talk more about Wi-Fi, I think, in next lecture. And LAN protocols are placed in the link layer. So if we look at the OSI model here, we have the data link layer here, and then we have the physical layer. The data link layer is typically divided into two. Let me just 1 second here. Do this. Right. Okay. Now the data link layer is typically divided into two parts: an upper layer and a lower sublayer. And the lower sublayer is this medium access control, and the upper one is the what's called the data link control sometimes. In the IEEE domain, this is called the logical link control. So this one is responsible for retransmission protocols and things like this. But there might be retransmissions even in the MAC layer here, as we will see. But anyways, if we want to look at the practical protocol, we don't look at OSI, we look at some practical protocol stack, and one of them are provided by IEEE, and they standardize the lower layers here, the LLC, the MAC, and the PHY layer. Yeah. So let's look at how this works now. What we will do is actually to look at this combo here. Sorry. So this combo is where we are aiming at now. So we'll talk a little bit about LLC over this MAC layer, which is called 802.3, and a little bit on physical layers attached to this MAC layer. Okay, so we have LLC on top of the MAC layer. So LLC has a protocol data unit, which consists of data it's gotten from above. So this could be an IP packet or some other packet that comes from the layer above the data link layer. So this is a network layer packet, protocol data unit. And this is then encapsulated into the LLC protocol data unit, which means some headers here. So there are destination and source, and then control bytes, and then this particular extension for a protocol. So this is, and everything here is then put into the payload of the MAC layer. Okay, so the MAC layer PDU has a MAC header, the LLC PDU, and then some frame check here. So a few things here though. So the destination and source addresses here, they are used for multiplexing. So LLC can support many layers above it, but it needs to know to which layer, from which protocol layer, from which protocol the data came from and where it should head, right? So the source and destination SAP addresses, they identify the protocol entity above the LLC, okay? And that could be many. One protocol is this protocol, the bridge spanning tree protocol that we will talk about at the end of this lecture. And another one could be this subnet network access protocol, or the SNAP. Okay, and that is used then to multiplex protocols that don't have their own SAP addresses. Okay, so the thing is that if we look at the destination SAP address here, it can identify a protocol at the other side, or it can say that we're going to use SNAP. And if we use SNAP, then we'll look into SNAP to figure out which protocol to use above. So this is a little bit of ugliness that one sees in practical protocols, that one has defined something and then, oh, we need an extension to this, and then one put in some ugly thing here instead of changing the address fields here. So that's how it works a little bit. Okay, so this SNAP protocol is actually important because many IP typically uses SNAP for. So when LLC is when this is an IP packet, then usually SNAP is used. Okay, that's what I'm trying to say here. Yeah. Okay. So if SNAP is used, then we have a little bit of extra header here, and that turns out to be important a little bit later. Okay, so Ethernet. So if this is Ethernet, what can we talk about Ethernet? So a small historical survey of this. Remember that we talked about ALOA, the random access method. So this was actually done for radio in the beginning. So this was deployed in 1970s, so quite a long time ago. A few years later, two persons, Metcalfe and Boggs, introduced what they called Ethernet. And they were inspired by ALOA, but they wanted to do this in a wired environment. So ALOA from the beginning was wireless, well, between the islands on Hawaii, right? So it's wireless. But then they wanted to do this also locally, for a local area network where you use cables instead. And what they used as a cable in the beginning was this coaxial cable. And then there has terminators at the end, so that the signals won't bounce back and forth. Basically, the signal that goes out here will be absorbed by the terminator here. So basically, one has a cable that we put some terminating impedances at the end, and then we use that as our medium. So instead of radio, we communicate over a coaxial cable. And then when one has a station here, one basically has a interface cable, and then drill a small hole into this cable, and then insert a thing in the cable that is able to tap, inject, and extract signals that are going over this medium. So this is how it was done in the beginning. And in the beginning, this cable was also yellow for some reason. So this. Sometimes when you get your routers home now, you see that you have a yellow cable, right? And there is a yellow port on the router. I don't know this for a fact, but I think it's a little bit of historical reason for this, going back to the old Ethernet with yellow cables. Anyways, so they did this in 1973, and in 1979 there was a standard developed from this. So basically this was technology that was just developed without being standardized, but in 1979 3 companies put together a standard that they called Ethernet 2 standard, or DICS. DICS stands for Digital Equipment Intel, I think, and X for Xerox. It doesn't matter so much. So this was then standardized, 79. In 1985, the first 802 IEEE 802.3 standard was released. So this is also called Ethernet, a little bit confusing. So we have an Ethernet which is standardized by IEEE, and an Ethernet which is standardized by DICS. But anyway, since these days, the IEEE standard, then a lot of improvements have been done to this with the fast Ethernet, gigabit Ethernet, 10 gigabit Ethernet, and now, 10 years ago, 40 and 100 gigabits Ethernet. So maybe there is something else here which is not on the slide. But there's been a lot of development here lately. And Ethernet is the dominant standard for LANs nowadays. So let's see a little bit on how this works now. So and from the perspective of 802.3. Okay, so this is the IEEE version of Ethernet. So it's a MAC protocol which means that it needs to do medium access control. And it needs to do medium access control here because we have several stations accessing this cable here. So how does it work? Well, it's one persistent CSMA CD with CSMA with carrier sense multiple access, CD collision detection. One persistent, meaning that if the medium is sensed as idle, then we transmit. If it's sensed as busy, then we sense until it's free and then we transmit. If a collision is detected during transmission, then we go into back off. So first of all, we abort the frame transmission and send a short jamming signal. Draw a random number R according to a binary exponential backoff scheme, and then weight R of these random number. R is random here, so we weight the random number of mini-slot times, T-slot, and start over again. So actually this is standard, more or less it falls into the category of standard CSMA CD, so it's just an adoption of this. Now this T-slot here is a critical parameter, the mini-slot time. And the mini-slot time here needs to be long enough for collision detection to be working, essentially, that we are able to sense the channel when we transmit, and if we hear another signal, we know a collision has occurred. But this means also that for a certain propagation time on the medium, we need to have a minimum length of the frame. Okay. And that minimum length of the frame is this mini-slot time. Okay, so the mini-slot time here is also the T-slot. Oops, let's do this. T-slot is also the minimum frame duration. Okay. And this minimum frame duration needs to be twice times the T-prop. As we saw in the previous lecture, this is required in order for collision detection to work. So for a 10 megabit system with a maximum cable length of 2,500 meters, 4 repeaters, amplifiers, one estimates that twice the propagation delay is about 50 microseconds. So this is back of the envelope type of calculations. So okay, so 50 microseconds, we need a slot time which is more than 50 microseconds. So what was done then was to say that the minimum frame length was chosen to be 64 bytes, which is 64 times, okay, so this is 64 times 8 bit. Okay, and a bit time is 1 over 10 to the times 10 to the power of 6. So this is equal to 51.2 microseconds. So we can specify the slot time either in microseconds or in the corresponding number of bytes that needs to be in the minimum frame. Okay, so this was done in the beginning. Okay, so this binary exponential backoff, how does that work? Well, we talked about binary exponential backoff before, so it's essentially the same. The only difference here is that we don't, after a while, we increase the backoff window. After a while, we don't increase it anymore. So the backoff procedure is like this. Before retransmission, attempt K. Okay, which means that we have had k minus 1 consecutive collisions. Then we choose R randomly from as an integer from 0 to 2 to the power of k minus 1. Well, small k here is equal to k as long as k is less or equal to 10. When k is greater than 10, it will be 10. Okay, so we cap that being maximum 10. So if we look at the backup window, how that increases, so here we have 2 to the power of k minus 1, which is the maximum value that R can take on. Then when we at the first retransmission, R can take on the value 0 or 1. After the second, it can take on 0, 1, 2, or 3. And now up to 7, 15, 31. And so this one exponentially increases until we reach 1023, and then we keep it fixed for the remaining for following retransmissions. After retransmission 16, we give up. So this is the max number of retransmissions. Okay. So after 16, we think, something is wrong. Maybe the cable is broken or whatnot. So we just give up. But going back here, so this is how backoff works. System will not attempt more than 16 retransmissions. Then one can show that at a high load, then the channel activity, if one looks at the channel, it will cycle between frame durations, an idle period of t-prop seconds, where basically different nodes are trying to figure out when the current transmission has ended, and then a number of unsuccessful contention periods, collisions, or like to t-prop, until one of the stations wins the channel and then transmits his frame. So that's how it would look like, essentially. Okay, we won't go into a lot of detail about this, and the reason why we don't go into a lot of detail is that this is hardly used at all today in modern Ethernet. So it's more of historical reasons. And this one also explains a little bit on how Wi-Fi works. That's why we talk about it. Okay, so the MAC frame for 802.3. So again, we have a higher layer, which is LLC. For IEEE, it's always LLC as the higher layer here. So we put in the PDU here, and then we put in some headers. And in the header, we have a preamble, we have a start of frame delimiter, we have a destination address, a source address, a length field, the data, and then possibly some padding, 0 bits here, and then a frame checksum. Okay, so the preamble here consists of preamble plus this part here. This is used for synchronization. Okay, so it's a physical layer synchronization essentially, and it consists of 7 repetitions of a 1-0 pattern, 1-0, 1-0, 1-0, 1-0, 1-0. And then this start of frame delimiter is 1-0, 1-0, 1-0, and then 1-1. Okay, so a station that listens to the median listens for this 1-0 thing, and when it detects this, it starts to listen to that until it hears 2 consecutive ones, and then the station knows, okay, the next thing that comes is the first bit of the destination address. Okay. Yeah, so the question was if this is susceptible to bit errors. It's true, but it doesn't actually detect the bits. It looks at the signal corresponding to this pattern of 1-0s. So we can think of this maybe that it's, maybe it's in the simplest case is something that looks like a square wave like this. So it looks for the square wave rather than trying to detect each individual bits. So you will then find, okay, there seems to be 0 crossings here, and then at the end it will be 2 1s, right? And then he knows, okay, here is the start of the frame, the first bit of the destination address. And then he starts to detect these bits for the destination address. All of this in the preamble is the same for all frames. So there is no need to detect the individual bits in itself. So basically, it's a correlation circuit that looks at this. That's a good question. So then there is the destination address, and these are the MAC addresses, these 48-bit network addresses or MAC addresses. There are 3 kinds: unicast, multicast, and broadcast. And unicast identifies a network interface card. It's its physical address. Or multicast, that means that we address several network interface cards on the LAN. Broadcast means that we address every network interface card on the LAN. And typically these are written as hex numbers. So F, or rather the broadcast address is the all one address. So F is 111, 4 ones. So FF is 8 ones. So here is 1 byte, 2 byte, 3 byte, 4 byte, 5 byte, 6 bytes. 6 times 8, 48 bits. Okay. So this is the MAC address you read off like a unit. Has this MAC address. The length field indicates the number of bytes in the blue part. Okay, and it's at the maximum. It's 1500 bytes is the maximum of the blue plus pad part. The minimum part of it is 46 bytes. Okay, so it has a minimum width here, and the minimum width here is in order to keep the whole thing to a certain duration that we need in order for collision detection to work. So the pad fields add 0 bits if needed to make the frame at least 64 bytes long. So the whole frame from the start of the destination address to the end of the frame checksum needs to be 64 bytes. Okay, and the 64 bytes comes from here, that we need the time duration of the frame to be at least 51 microseconds. And we need that in order for collision detection to work. Okay. Then the frame checksum here is a 32-bit CRC. Okay, so these are the 32 bits that we get out as parity bits from a CRC. And the CRC covers the whole frame except the preamble, and so these bits are never used in order to produce the CRC, and which is quite reasonable because we don't care about these bits. We know what they are already. So but we care about the destination, source address, and every other bit here. Okay, any questions on the frame format here?
Question on something else.
Yeah.
I missed the lecture, so I think that might have been covered before.
Mm.
But a collision, what's that?
A collision is when two stations access the medium at the same time, which is possible because they are not 100% coordinated, which is impossible in this scheme. Okay. All right. Now there is no need for multiplexing tags in the headers here because there is only one upper layer to the 802.3 MAC, and that's LLC. So it knows where it should deliver its payload. Okay. The DIX frame, which is the early Ethernet. Okay, so the earliest version of the Ethernet is called Ethernet 2, right? So, you know, that's weird. It's probably an even earlier version that's called Ethernet 1. But anyways, Ethernet 2, and it's also called Standard Ethernet in Furusan. This was the early standardized version of Ethernet. It looks exactly the same as the IEEE frame, except for this field. This in IEEE, this is the length field. In DIX Ethernet, this is the type field. Okay, so DIX stands for these three companies that got together and wrote the joint Ethernet specification. The type field is used to identify the upper layer. Okay, and the upper layer could be IP or ARP or something like this. So this is the multiplexing tag. Okay, so above the DIX Ethernet we can have many different upper layers, while for IEEE Ethernet we only have LLC. Okay, so we need a multiplexing tag for DIX Ethernet, and this type field then identifies the upper layer protocol. The type field starts at 0600 in hexadecimal, okay, which is actually greater than the minimum value, greater than the maximum value of an 802.3 length field, which is 1500 in decimal or 05 DC in hex. Okay, so this is important because now if I'm attached to a medium and I get a frame, I can inspect these 2 bytes, and depending on the value of these 2 bytes, I can say, okay, this is a DIX frame or this is an IEEE frame. So I, as a receiver, can distinguish these two things by just inspecting the type field. And this is important because on the same medium, it's actually allowed to transmit both types of frames. Okay. So a receiving network interface card can then inspect this length or type bytes and then determine whether it's an 802.3 or a DIX frame. Okay. And then 802.3 now, how many bytes, upper layer bytes can it, network layer bytes can it support? Well, it can support 1492 bytes. And why is this? Well, if we go back here, we see that we can have 1500 bytes of payload here in an 802.3 frame, but in this payload, we have 8 bytes of control information due to the LLC, and the above LLC, we have this as a payload. So if this is the IP packet, then this has to be less than 1492 bytes if we use 802.4 IEEE. Okay, so that's the maximum IP packet we can use if we use IEEE. But if we use DIX, okay, so if we use DIX, then actually this whole thing here could be an IP packet. And then we can support 1500 byte in this case. So IEEE can support slightly smaller IP packets than DIX, 8 bytes difference. But anyways, due to this fact, most IP traffic is actually using DIX frames. So this old standard, right? Not the IEEE standard. But if one is using IEEE standard, then okay, we have to use smaller IP packets. Right, so this is a little bit of a quirk, but anyways. So let's look a little bit about the physical layer for 802.3. So in the old days, there was this coaxial cable. So it's like a cable, I don't know, maybe 10 millimeters thick, like this. And if you know a coaxial cable is kind of bulky, and you cannot bend it arbitrarily, and things like that. So it's not really nice to work with. So there was a version with using a more thinner coaxial cable, and so. And this was an improvement, but still not very good. So anyways, this was quickly abandoned, or quickly. After a while, this was abandoned in favor of twisted pair instead. So this is a twisted pair cable. We'll send this around so you can have a look at this. You've probably seen this many times before, but anyways. So we have, this has now been improved to work with different. Okay, so before we actually go to this, so we had a medium which was a thick coaxial cable, 500 meters maximum, and the topology was a bus, meaning that everyone hears everybody's transmission. Then there was thin coaxial cable, still a bus, and then was twisted pair in star topology. So what does this mean? Well, if we have a hub or bus topology, what it means is that everything which is attached to the medium hears every transmission which is ongoing on the medium. That's a bus for you, right? So which means that we have one domain here where collisions can occur. So this is the old day. Nowadays we use switches instead, which means that we have each device is hooked up to one of the ports in the switch. So one of the devices to one port, the other one to another port, and the third to so forth. Inside these ports, we have buffers. buffers that buffers incoming traffic and buffers outgoing traffic. So either this cables is full duplex, which is the common case today, or it's if it's full duplex or half duplex. Full duplex is most likely today, which means that data can go in both directions over this cable without interfering with each other. And in that case, there is not the need for medium access control anymore, because all the collisions are taken care of by the switch. Okay. So by introducing the switch, we separate these collision domains, which means that if we want to add more things to our LAN, we basically just buy another switch, or we plug it into one of the, this is a 5-port switch. I mean, if I need 6 devices, I just buy another switch and replace that, and then suddenly I have 6 one. But performance is not affected too much, because there will not be more collisions just because I add another port in the switch. However, if I added another device here on the shared medium, there would be a bigger chance of collisions. So better scaling with switches and less collisions. So this is why these are used now in practice. So this is what's used today. So I will send around the switch. You've probably seen this before also, but anyways. So 100 megabit Ethernet was introduced a few years later after 10 megabits. And to reserve compatibility with 10 megabit Ethernet, so we can run 10 megabit and 100 megabit Ethernet over the same medium. One kept the same frame format, the same interfaces, and the same protocols. One reduced, however, the maximum length of the medium. Okay, so instead of 500 meters or whatever it was, we have now a maximum segment of 100 meters. So 100 meters of that cable. Which means that we reduce the propagation delay, which means that we can keep the same minimum frame length still at 64 bytes, which is 5.12 microseconds as a slot time. 5.1? It's probably should be 51 microseconds here, I think. No. So we can have this as our slot time, which is 64 bytes is now much shorter than it was before. It was 51.2 microseconds when we had 10 megabits. It's a factor of 10 less when we have 100 megabits. Right? You get more bits per time unit. But this is still okay, since we have reduced now the propagation delay over the medium. So collision detection will still work. But collision detection is not really needed, because we basically go to these switches and then medium access control is not needed. But the bus topology and the coaxial cable were abandoned. And that now gigabit Ethernet is quite common. I have one at home, probably you do too, perhaps. So the gigabit Ethernet is quite common today. Now, going from 100 megabits to 1 gigabit is a factor of 10 in data rate, which means that we need to do something about the frame duration. So the minimum frame length was now extended from 64 bytes to 512 bytes, which then corresponds to 4.1 microseconds, which is similar to the slot time we had for 10 megabits per second, which is 5 microseconds. So essentially, we, instead of reducing the length of the segment, we extended the minimum frame length in bytes. And then everything works. There are some other inventions done here. So the frame structure is preserved, but essentially this CSMA CDA is abandoned, because we have now switches taking care of that. We've seen extensive deployment of this. And then we have 10 gigabit Ethernet. Also now, probably not, this is more for longer connections, as you will see. So mean, except for this one, it's like 300 meters to 10 kilometers. But we have here maximum lengths which are quite long here. So now one can question, is this still a local area network, right? Because it's quite long in that sense. But it's still called a local area network for some reason. All right, but for 10 gigabit Ethernet, there is no CSMA CD anymore. Okay, and it's only defined for full duplex point-to-point links. And yeah, I mean, it can use different types of file layers. I won't go into the detail here. And then, of course, we have, it's not, I don't have a picture of this, but there is 40 gigabit and 100 gigabit Ethernet now also available. I mean, it's not deployed in offices and things like this, but it's for longer connections. Not so much. Okay, so when we then connecting in several LANs, so if I, okay, so if we have several local area networks that we would like to connect to each other, how can we do this? Well, there are three main things we can do. We can use repeaters, bridges, or routers. Okay, so if we have two LANs here, one red and blue, and then we would like to put something in the middle here to connect these two things. Okay, then we have these options, like a repeater, and what the repeater essentially does is that we can think of that as basically just connecting the two, electrically connecting these two things. Okay, so this would be a hub or a repeater. Yeah, it basically just connects it. It could be a bridge, which we will talk more about later on, and that's a device where we have a protocol stack in here, where we at least have a MAC layer. So data that goes in here goes up and it's processed and goes down here and then attached to this one. So we have here a MAC layer device switch. I didn't spell that very well, but anyways. And then we have routers, which are connecting devices here, where we have where we have physical layer, MAC layer, and a network layer. So data actually goes up and down like this, connecting points like that. So we can connect LANs either on the physical layer through a hub or a repeater, or through a MAC layer through a switch, or through a router where we have a network layer also. Now, for sure, you can read about layer 3 switches, okay, which is not what I'm saying. I'm saying here switches are layer 2 devices, which has only 2 layers in them. But you can for sure read about 3-layer switches. And here, this is the thing, that switch, the word switch is not well defined. But to keep it simple in this class, when talking about the switch, it will be a layer 2 device, which has a physical layer and a MAC layer, maybe also a data link layer. But anyways, a MAC layer, physical layer, and a MAC layer, while a router would have a physical layer, a MAC layer, and a network layer. All right, so pros and cons with this. Repeaters are simple, but the problem is that there's a signal which is sent on one LAN is also visible on another LAN, which creates more collisions. And bridges are much better for doing this. Routers are even better perhaps, but more complicated, and for sure more delay in it. All right, any questions on this? Okay, so let's talk about link layer bridges here. So what are these? Well, I mean, if we have a host and another host here. We have a host here which is connected to a LAN, and we had another host which is connected to another LAN here. Suppose in the left-hand side here, we have a host, which means that it has a transport layer, application layer, transport layer, whatnot. But then there is a network layer for sure. And suppose it has a data link layer, which is an IEEE layer. So it has an LLC and a medium access control, and it's actually Ethernet here. And then it's a physical layer. It's a 10 megabit Ethernet. That's what it is here. So this is a 10 megabit wired Ethernet, this local area network. Now this host would like to talk to another host, which has another protocol stack, still IEEE, but it has a Wi-Fi MAC layer, and then a Wi-Fi physical layer here. So this is actually a wireless LAN. So how can a host on a wired LAN talk to a host on a wireless LAN? Well, we need a device in between these two devices. And here, a hub or a repeater is not possible, right? Because it's two different technologies here. Here we have something in the cable, and here we have something on radio. So data that goes from this host actually goes down over this physical layer, and then we have this intermediate device, which is a link layer bridge. So there is some data coming in here, for instance, using the same physical layer as the physical layer is on the LAN here, of course. There is a MAC layer, and then it pops up into the LLC layer here. But then it can go down on the other side here, where we use another MAC layer and another physical layer compared to what's on the left-hand side here, and then transmit data on this one. Okay. So this link layer bridge here can connect two LANs with different technologies. And it can do this in a transparent manner, such that the hosts don't even notice this. Okay, so that's the magic behind this. So we don't have to, the data traffic that goes down here doesn't need to be different if it goes to another host on LAN 1 or it goes on a host to LAN 2. It's the same packets. Okay, and likewise if it goes the other way, like this. So let's see. Right. Okay. I think it's a good time to take a 15-minute break, and then we continue after the break. Okay.